Okay, so just finishing up answering some questions in chat. So basically, because uh, uh, because the online grading takes a long time, pretty much there's some issues with I can't remember exactly when the deadline is. It might be like the last day of classes or something like that. But basically, you shouldn't be too worried about your uh, you should be too worried about the grades because we're gonna we'll take it easy on you, because we understand that it's not exactly an ideal instruction environment, so you don't have to worry too much about the grades. We'll make sure that we're maximally lenient in that way. So anyway, a couple of things. So people were asking about the MATLAB. I will. Yeah, May 12th. I thought that was the deadline for this. Yeah, I can post solutions to second exam actually later today. So I know at least one of the GSS leaders went over solutions to the exam. So I think so. She did that yesterday. So you can have a look there. I'll post the solutions a bit later today. I can upload those. What was I saying? Oh, yeah. So basically, we're gonna finish by the end of lecture tomorrow. We'll essentially be done with all the material that I wanted to discuss. So I plan on next week's lecture will be. Plan is to tidy up what I need to. It shouldn't be much, and then to do review for your final exam, which I'll be posting in a similar fashion to your exam too. So I'll post it, and you will have a few days to turn it in, maybe like 4 or 5 like last time. Is the idea. So, maybe I wanted to at least finish or start and finish a quick discussion of matrix exponentials before moving on. So the idea is that there's a quantity called a matrix exponential that is associated to solutions of linear systems. So this is a quick aside. So typically this is actually done before the eigenmethod stuff, but I did the eigenmethod stuff first because once you know the eigenmethod stuff, I can easily talk about matrix exponentials. There's no reason to go through a lot of the theory here. So the idea is I have some matrix equation. X prime is equal to ax, where a is some constant matrix. It's n by n typically. Then if phi is the natural fundamental matrix, you don't have to worry too much exactly about what this is. It's analogous to the natural fundamental solution set for a higher order equation. The idea is that this phi solves the following differential equation. So phi solves phi prime is equal to a phi, where this is now a matrix differential equation. It works in the exact same way. I mean, technically this is also a matrix differential equation because column vectors are matrices, right? They're just a particular type of matrix. So in this case, we can actually say that when a phi satisfies this, it turns out such a matrix phi satisfies the following properties. Okay, so the properties that this thing satisfies are one, that phi of t plus s. So this is a differential equation. So technically, this is a thing that depends on t. I've just suppressed the notation here. So really, this is a phi of t here, right? Just like these vectors are vectors that depend on t. So anyway, the properties that this thing satisfies are that phi of t plus s is phi of t times phi of s. And the second thing is that phi of t times phi of minus t is actually equal to the identity matrix. Okay, the identity matrix is the thing that for matrix multiplication acts like 1, right? So multiplicatively, this thing acts like 1. So I get these two properties. And these two properties are always true, or always hold for all t here. So what do these two properties tell me? Well, these two properties are very reminiscent of what an exponential thing would satisfy, right? So like an e to the at satisfies both of these types of properties. Okay, but because the a in question here is actually a matrix, how we write this is e to the big AT, or your textbook writes it as e to the TA. Okay. All right, and this thing is called a matrix exponential. So what we do is we say that this phi is called a matrix exponential. So phi of t is, or maybe I should write it the other way. So what is defined to be phi of t is this e to the ta, and this is the matrix exponential for a. Okay. So in a way, this is really just notation that we're using because these properties say that this phi acts very much like an exponential thing. Okay, and so that's where this notation comes in, and that's why we call this thing a matrix exponential. Okay, so a couple of questions then. So given a matrix equation, x prime is equal to ax, how do I compute the matrix exponential e to the ta? Well, so going back here, in order to find this e to the ta, really I'm solving a matrix differential equation, but I don't really know how to directly do that. Now I could go through the theoretical underpinning of what exactly this means, but now that we know the eigenmethod stuff, we can actually cut straight to this. So I called phi the natural fundamental matrix. That word natural here is doing doing some work. We have talked about fundamental matrices. So what was the fundamental matrix? So the fundamental matrix was phi of t, or sorry, c of t. So the answer to this question is using eigenmethods, which means that for us, we're going to do this where a is a 2 by 2. The thing is that this process, as I mentioned previously when I first talked about this, can be done for larger matrices than 2 by 2s. Okay, but the thing is that for matrices larger than 2 by 2, the eigenmethods doesn't always work, and so you have to use this more general method. But since we're only going to do 2 by 2s in this class, eigenmethods are always going to work for us to find what we want. So using eigenmethods, find the fundamental matrix which is c of t. Then e to the ta is just the fundamental matrix times the fundamental matrix evaluated at 0, except I take its inverse. Okay, so this is important. This is a quick way to compute matrix exponentials if you know the fundamental matrix C. Okay. And of course we found this using eigenmethods previously. So how does this work? Let's do an example of this. So let me pick one of our examples from last time. Example. So find our compute e to the ta for A, which is the matrix 3, 2, 2, 3. Okay. So from last time, we actually constructed a fundamental matrix for this thing. So from previously, we saw that C of t was e to the t, e to the 5t, minus e to the t, e to the 5t. All right. So this came directly from the eigenmethod stuff where we constructed two eigensolutions, right? And that's what forms the columns here. Okay. You can actually read off the eigenvectors here, right? 1, 1, and 1 minus 1 were the two eigenvectors associated to those eigenvalues. The eigenvalues were 1 and 5, right? So you can actually read all that info off directly from the fundamental matrix. Okay, so using this formula, this is what I plan to do. I look at C of 0. So evaluating C of 0, I get e to the 0, e to the 0, e to the 0, e to the 0, but there's a minus sign here, so this is 1, 1, minus 1, 1. Okay. And now I need to compute C of 0 inverse. What is that? So, quick reminder, how do I compute the inverse of a 2 by 2? So, the inverse of a 2 by 2 is the following. Thankfully, there's a quick, handy formula for the inverse of a 2 by 2. Right? This doesn't work nearly as nicely for larger matrices, right? This is essentially the like adjugate formula if you've had 240. So what is this? So remember, this is 1 over the determinant, so that's 1 over AD minus BC, times a 2 by 2 matrix, which is, how do I remember to do this? I swap the entries along the main diagonal. So A and D get swapped, and then the entries in the off diagonal get multiplied by minus 1. Okay. So, remind you, C of 0 is 1, 1 minus 1, 1. Okay, so then C of 0 inverse, which is 1, 1 minus 1, 1 inverse, is, according to this formula, 1 over AD, it's 1 minus 1 times 1, so 1 minus 1, that's 2. So this is 1 over 2 times D and A get swapped, but they're the same thing. Minus B is minus 1, minus 1 is 1. So there it is. Okay. Thus, our matrix exponential, which is computed using this formula, C of t, C of 0 inverse, writing this out as matrix, this is, or matrix multiplication, this is e to the t, e to the 5t, minus e to the t, e to the 5t, times 1/2 times 1 minus 1, 1, 1. Alright. So, multiplying these out, what do I get? This is 1/2 times e to the t plus e to the 5t minus e to the t plus e to the 5t in this entry minus e to the t plus e to the 5t and e to the t plus e to the 5t. Yeah, that's right. So just checking here. So the 1/2 I'm keeping outside. So this is e to the t plus e to the 5t. Then minus 1 e to the t plus 1 times e to the 5t. Yep. Minus 1 e to the t plus e to the 5t. Yep. And minus e to the t times minus 1. So that's e to the t plus e to the 5t. Yep, that's it. Okay. All right. So here is my matrix exponential. All right, note that despite this notation, you might have a temptation to say that if A is, say, A11, A12, A21, A22, then e to the ta, you might say, is just e to the a11t, e to the a12t, e to the a21t, and e to the a22t. But if that was the case, there'd be no reason for this discussion. So this is most certainly not the case, right? These two things are definitely not equal. Okay, and you can just see that by looking at this thing that we've computed. So this is how to find a matrix exponential. I'm not going to go over other examples since this one works perfectly fine on its own. You can actually go back and look at the previous video, and you can try this if you like for those other two examples that we did, those other two matrices that we did. You can try this exact thing, and you'll find the matrix exponentials for those other two matrices. Okay. So that's more or less all I wanted to say about matrix exponentials. So there's, as I said, theoretically there's a really good reason why we talk about them and why they're nice. But since one, some things are being truncated, and two, for our purposes, we're not actually going to make use of them. This is more for just having you be familiar with them and know that there is a more general method that applies to larger matrices when eigenvalues or when eigenmethods don't work. So there is another way that a matrix exponential can be computed, but I'm not going to get into that just because we're not going to use that really in this course. Okay, so I come to what's going to be our last major topic, which is the classification of phase plane portraits. And I suggested that all of you have a look. Phane. What is a phane? Phase plane portraits. So I suggested that all of you have a look at the notes. Oh, I'm writing off screen. So in the notes, this begins on page 9. So page 9 in the linear, I believe it's the linear planar systems section in chapter 3. So chapter 3, linear planar systems, which I believe is the 7th thing. So this is in 3.7. And page 9 is where this discussion begins. You should probably have a look at that while I'm talking about this, because I'm going to refer to pictures. I'm going to draw the pictures here, but my pictures are necessarily going to be much shittier than the pictures in the textbook. Because, obviously they using computers to generate theirs, and I'm not very good at drawing anything. So those pictures are going to be a lot nicer than my pictures. What is it that I'm talking about? So we talked about phase plane portraits before at the very beginning of the semester when we did first order equations. So the idea is exactly the same. So we have a system. So idea. We have a system of first order differential equations. So linear, obviously, I forgot that word, but so the system is derivative Oh, if I'm not going to use x, that's fine. I'll use t. So a derivative with respect to t of a vector of unknown functions xy is a times xy. This is exactly the same thing that we've been writing forever. I'm just using x and y here instead of x1 and x2, right? So this is literally exactly this equation. So whether you write it like this or like this, it doesn't matter. The idea is you have a system. It's given to you as this matrix or this differential equation involving the vector x of unknown solutions and this constant matrix A. And I want to sketch phase portraits for it. So I want to sketch phase portraits for it. Now, when we did this earlier in the semester, you might remember that the thing we were calling phase portraits, whether you identified it as the sketches in 2D or really the thing that we called the phase portrait was this thing, right? So you drew, I recall, this sort of thing, right? And maybe you did that, and yeah. So you had some line that looked like this. The points were the equilibrium points, or the equilibrium solutions. And then these arrows indicated behavior of the solution. So this was actually telling you how the solution was moving as t goes to infinity, as t goes to minus infinity. And we used this. So we used this in chapter 1 to discuss long-term behavior of solutions. And our solutions in chapter 1 were some unknown functions y of t. And what we meant by long-term behavior of solutions was we were considering things like what's the limit as t goes to infinity of y of t, what's the limit as t goes to minus infinity of y of t. Okay. And these questions could be answered directly from looking at this line, right? Now, you might remember, like I said, I had you guys sketch out something that actually looked like a graph of something. That was interpreting this, of course, as this, even though we drew it horizontally, typically, this was actually y values, right? These were the values of the function y. And so this is what we did in chapter 1. Right, then this was our phase portrait, and from this, didn't need to draw anything else. You could discuss the long-term solution. So, namely, what these limits are, what this thing was doing asymptotically, right? Is t goes to infinity or t goes to minus infinity. Now, how is that going to change here? So here we had a single unknown function. Here we have a vector of unknown functions. So there's a reason why we have the switch in notation. Just to illustrate what it is that's going on. So again, so returning to this equation, the idea is that a phase portrait should allow me to discuss long-term solutions to, or I should say long-term behavior, really. So long-term behavior of solutions to the above. Right, so here's a differential equation. Long-term behavior of solutions to this thing should be describable from phase portrait. That's kind of the point. So what does a long-term, or what does the solution to this thing look like? It's a vector x of t, y of t. Right, here's what a solution to this thing looks like. Well, the idea then is, as you know, of course, I can view a 2 by 1 vector like this as an ordered pair. Which is a point in the plane, right? So for a single t value, I have the point in the plane x of t, y of t. And so the idea here is at some other t, right? Maybe they're over here, right? Maybe here's my, so this is x of t sub 1 and y of t sub 1. The idea is that as t varies, this traces out a curve in the plane. Okay, so this yields curves in the plane. Okay, so then the main idea is to come up with a way to sketch the behavior of these curves in any case. So that is in any case in which I might find myself, right? And of course, all this depends on A, right? All depending, in this case, on A and its eigenvalues and eigenvectors. Okay. So, going back, in chapter 1 when we did this, our picture was one-dimensional, right? It was on a line. So every piece of data that we drew in here was on this line, and this was all we needed. Here, necessarily, because our solution is actually an ordered pair of unknown functions, right, then the pictures are going to be in the plane, and that's why they're called planar systems. So the idea is to come up with a way of sketching long-term behavior of these curves in a similar fashion. But unlike here, where there were only a couple of quantities we had to check and only a couple ways your picture could look, really, here there's going to be 20 cases. Now, so it turns out there are 20 cases. All right, so there are 20 possible cases here. Note we're doing this, as I said, for A is a 2 by 2, obviously, because the dimensions have to match up here if we're talking about planar systems. Now, don't freak out too badly about this 20 cases bit, because you would have been doing this in class and you wouldn't have had access to notes. So you would have been expected to know these 20 cases without referencing notes. And it's not that we're like grinding you down or doing anything unfair here. There's a way that these cases play out that you don't have to just remember 20 in a row and without any context or anything. So there's a reason why this shouldn't scare you too much, because the 20 cases are nicely separated here. Okay, so before I go on, these 20 cases, as you might expect, have to do with the cases in which you find this eigenvalue, or the eigenvalues of A. So we know that there are 3 main cases, and each of those has subcases. So the idea. Okay. So what is the big idea? The solution to the previous equation can be written as the following. So now that we know matrix exponentials, I can write it out like this. So our solution to the previous equation can be written as the vector x, y, and we can think of that as the matrix exponential e to the ta times our initial values. Okay. So remember, those initial values are so x of 0 and y of 0. I don't think I actually wrote out the initial conditions. That's my apologies. So in the previous page, I wrote equation here. I did not write initial conditions. Okay, so I'm writing them now. So that the problem in question is an IVP, right? This is something you always considered when you were doing phase portraits. Okay. Now, since A is a 2 by 2, there are 3 main cases for the roots of its characteristic polynomial. All right, so there is main case 1. P of z has 2 distinct real roots. Case 2, P of z has 2 distinct complex roots. And case 3, P of z has 1 real double root. Okay. Now it turns out that in general, I can write out what the matrix exponential is for these things using either, the textbook uses either hyperbolic cosine and hyperbolic sine, cosine and sine, or a different formula for the real double root. We don't have to do that. So the only thing that we have to do is remember that in each of these cases, we actually know how to use eigenmethods to find this matrix exponential or just the fundamental matrix C. Okay, so what do we do here? How do we classify all of these cases? So it turns out this splits into 5 cases. So this is 5 cases. Okay. Should say those are like 5 main cases. And then there's, I should say, there's 6 cases here. In this case. And then there's a remaining I guess there's 6 total here, where 20 comes from the remainder null cases, I should say. Um, so that doesn't look like it's 20, but it's a total of 20, and I'll show you how here in a second. These are the main ones, though, that actually have pictures, so the textbook doesn't even draw a picture for some of these. So what does... this is not the best way of actually remembering these. The best way of remembering them is to just go piece by piece to write out what it is these things are referring to. So I have the two distinct real root cases. I think I'll do that first. I think that makes the most sense. So mega case 1, looking at the subcases. So let's say that our characteristic polynomial has two distinct real roots. Notice that I actually just wrote p of z. I didn't even write p of a here. So I can fix that, although it doesn't change what I'm saying materially very much. There's a reason why we reuse the same terminology. So let's say that our characteristic polynomial for a has two distinct real roots. The cases that we're going to consider, so the cases that we're going to consider have to do with the relative size of the eigenvalues. So if you have two distinct real roots, a real root of your characteristic polynomial is a matrix. That's eigenvalues lambda 1 and lambda 2. Lambda 1 is not equal to lambda 2. That's what the word distinct means. So here I have two distinct real roots to this characteristic polynomial, lambda 1, lambda 2. I just think of the ways in which these can be arranged. Okay, so I consider the ways that, so consider the possible arrangements, I'll call them, of lambda 1 and lambda 2. Okay. Now, why is it that I'm wanting to talk about arrangements of lambda 1 and lambda 2? Because I know that there's a very simple way I can express my general solution in using lambda 1, lambda 2, and the associated eigenvectors, right? So what are my possible arrangements of lambda 1 and lambda 2? So there is the, so one is, one's positive and one is negative. Okay, so that's a possibility. Okay. What else? Well, both could be positive. Both could be negative. For ease of notation, we'll say that lambda 1 is always the smaller one. Okay, what are the other possibilities? Note that I didn't say anything about one of them being 0. Right, so right now I have two real numbers. So think, this is not really even a fact about eigenvalues. This is just a fact of when you have two real numbers and they're two distinct real numbers, what are the possible ways that those real numbers can be arranged? I mean, one could be positive, one could be negative. Both could be positive, both could be negative. One could be 0 and the other negative, and one could be 0 and the other positive, right? So you could have lambda 1 is less than lambda 2 and lambda 2 is 0. Or you could have lambda 1 is 0 and lambda 2 is positive. So quickly going through here, not referencing the notation I've used, I have, first case is one's positive, one's negative. Second case is both are positive. Third case is both are negative. Fourth case is 1, 0 is 1, 1's negative, and the other case is 1, 0 and 1 is positive. Okay. Why do the possible arrangements of this matter? Well, this is a bit of the theoretical underpinning that you can all understand how this works. So recall, the general solution in this case is x of t is c1 e to the lambda 1 t v1, or v1 is that eigenvector associated to lambda 1, plus c2 e to the lambda 2t times v2. Now, regardless of what these eigenvectors are, they are constant vectors in the sense that they don't depend on t. c1, c2 are arbitrary constants, and so if I want to understand things like the limit as t goes to infinity of x of t and the limit as t goes to minus infinity of x of t, if I want to understand these two things, the only thing that matters is the relative sizes of lambda 1 and lambda 2. That's why this discussion exists. Okay, that's why this discussion is going to tell us how this works. Why? These are exponential things. Right, so imagine I only had one at a time, right? Lambda 1 being positive or negative is going to tell you whether this thing limits to 0 or whether it limits to infinity. Okay. Similarly for the other term, because it involves exponential terms. And the relative sizes of lambda 1 and lambda 2 are going to tell you everything you need to know about, as t goes to infinity, whether, looking at this solution broken up in this way, whether I tend toward one or the other term, right? Okay. So let's go through this in the time that I have here. So the first case, let's do this. So recall, whenever I refer to anything, I'm thinking of this. Okay, I'm thinking of this solution. So we're still in case 1. So our solution still looks like I just wrote. Okay. Oh. Okay, so there it is. So in case 1, where 1's positive and 1 is negative, what is it that happens? So if lambda 1 is negative and lambda 2 is positive, just looking directly at this thing, when you take the limit as t goes to infinity of x of t, which term dominates? Well, note that non-zero solutions on the line x equals c1 v1 in the plane will approach the origin as t goes to infinity, while non-zero solutions on the line x equals c2 v2 will move away from the origin as t increases. What does this mean? So what this means is that we are encouraged to draw a picture. Okay, so the picture that we draw is going to be the following. So I'm going to have typical picture of plane, and I'm going to split plane into pieces. This is just a general arrangement. Of course, your pieces are not always going to look exactly like this if you're scaling everything in a particular way. The idea, though, is that I have a picture of x of x is equal to c1 v1 and x is equal to c2 v2. So the idea is that I use v1 and v2 to determine vectors, or rather lines. Okay, so I have lines determined by v1 and v2. So to say what I'm writing out here, this line is the line associated to the eigenvector v1, meaning I'm considering all possible scalar multiples of the vector v1, which is why I get a line and not just a vector or a point. Same thing for v2. I'm considering all scalar multiples of the line v2. And so for all of these where this is relevant, this is not going to be relevant in our next super case, but in this first case, the first step is to draw these two lines associated with the vectors. Again, as I said, if you're doing this for a particular problem, your v1 and v2 are not always going to be exactly arranged like this, but you're going to have two vectors arranged like this in some way. And the idea is that these eigenvectors are essentially playing the role of the equilibrium points in the chapter 1 case. Okay. So these are basically playing the same role as those equilibrium points. So these are like the barriers that your solutions that you sketch are not going to cross. Okay, and so as I said here, non-zero solutions along this line are going to approach the origin as t goes to zero, or sorry, as t goes to infinity. Okay, so these are going to go to the origin as t goes to infinity. And why is that? If they're along this line, then your c2 is 0, so this term is not there, right? And as t goes to infinity, lambda 1 is negative, right? So the limit as t goes to infinity of just this term where lambda 1 is negative is going to be 0. That means that points along this line get pushed towards the origin. Points along this line get pushed towards the origin. And so we have arrows that we draw indicating exactly that. Okay. Okay. Furthermore, on the other line, if you're on this line, that means that this term is 0. So 0 out that term. Look just at this second term. As t goes to infinity, well, lambda 2 is positive. So this term is going off to infinity. So any points along this line are getting pushed off towards infinity. And so I have arrows drawn in this way. Now, the idea is that from this picture, depending on the case you're in, sometimes it can be confusing as to how to do this from the picture, but this typically works if you're careful. The idea then here is to fill in a picture that is consistent with these arrows. So what that means is that what might a solution that is not along one of these lines look like? That is, what if I have a general solution that looks something like this? Okay, so I have solution looks more or less like this. So, for some values of C1 and C2, so this is what my solution looks like. What would its curve look like in the plane? Following these arrows, it would maybe look something like this, where I have a curve doing this. And here is another, what's called an orbit. Here's another one. Maybe here's another one. And again, note the direction my arrows are going to indicate that they are consistent with the arrows that I've drawn along those lines. So then this is what my phase portrait would look like. Now the question is, what is this telling me? So this particular example is done at the top of page 10 that I talked about. So this is the top of page 10. So what is this actually telling me? What this is saying is the long-term behavior of the solution. So I claim this tells me that the limit as t goes to infinity of x of t is actually this line, this piece, okay, of the solution. So this goes to, I should say, approaches, maybe I should just say, is equal to c2 e to the lambda 2t v2. Now you might protest and say, wait, isn't that equal to infinity? Yes, but what's more important is that you recognize that it's this piece of the solution that's dominating. Okay, and so what happens is you're going along here, depending on where you started, you're going along, and as t goes to infinity, you're eventually approaching this line. Maybe here you're approaching the line in this way. But notice how all of these solutions are approaching that line as t goes to infinity. So as always, the arrow direction indicates t increasing, so t going to positive infinity. And the limit as t goes to minus infinity of x of t is the other term. Right? So it's c1 e to lambda 1t v1. That's moving backwards, right? So as I move backwards, I'm going from being along this line to being along the other line. Okay. Makes sense. And so, I have thus described the long-term behavior of these things using this picture. Okay, and this is what I'm going to do for every single one of these cases. So that's more or less all I'm going to say right now, because I'm almost out of time. We started a little bit late, so I think I'm almost exactly out of time here. So I will cut it short, and we will finish this entirely tomorrow. So we'll finish this entire discussion. I'll do a few examples, and then that will be that. That will be the course. On Tuesday, like I said, I'll tidy up. If I have to answer a bunch of questions and don't quite finish all the cases, I'll tidy that up during Tuesday's lecture, and then I will go through kind of a list of what you can expect to see on the final exam, and then your final exam will be, or rather rather than saying what you should see on the final exam, since you're going to have days to take it, it's not exactly going to be like a surprise or shock. Maybe instead I'll just, what I mean by that is I will highlight some important bits of the notes that you should have a look at. That makes more sense given our format. So, looking at some last questions. Yeah, I believe, like I said, the aforementioned deadline is May 12th. This is the deadline to choose whether or not you're doing pass, fail. And I believe, the way that it's done, that's entirely on your end. We don't see that, so we just input the grades as normal. Your grades will definitely be, like I said, a little nicer just by the numbers than they would have otherwise been because of all of this. So you shouldn't be too freaked out over worrying about having a low grade, unless you just did absolutely horribly on the first exam. If you're worried about it in that case, even in that case, really, I'm gonna take it easy on you all, so it's okay. Is there any shot you're still going to post a method undetermined code? Oh, yeah, I guess I totally forgot to do that. Yeah, I mean, I could still do that. I could still record one of those. Probably have to happen over this weekend though. But yeah, that's something. Anyway, I mean, I'd let you know when I do that. Let's see. Uh, yeah, I think that covers everything. I'm just reading through the questions. Oh yeah, so I'll remember to post the solutions of the second exam, so that you can see those. That way, I mean, this was kind of my plan for you at least seeing, how you think your solutions on the second exam stacked up before you get your grade. Well, even after you get your grade back, right? Because your grade, I looked into having the TAs actually like annotate grades, like annotate like your turned in like PDF, um, and it turned out that it was going to be like an absolute nightmare to set up, so I decided not to do that. Uh, yeah, in fact, I can hold on. I'll post them right now. Um, I think I have them here. Uh, let's see. I think I have them handy on this laptop. Oh, maybe not. Oh. Um, oh, maybe I thought they were handy, but they're not. Uh, uh, Searching for them. Well, at any rate, I'll have to look here in a little bit. But yeah, I'll post those here in a little bit. All right. Well, anyway, so that's the plan going forward. So I will see you all tomorrow. Like I said, I'll post those solutions. I'll try to. I'm gonna go over to my desktop here in a second and print the or and look for them because I just sent them out a couple days ago. So anyway, I'll see you all tomorrow.